Of course. Give me
Thank
a
you very
few
much.
seconds, please. I just need to.
The facilitator is joining us from Canada. He was one of the facilitators in the last HPC.
I
Okay,
don't know if you can see me.
thank you very much.
Good morning. Hello, everyone.
Okay, so you can start.
Okay. Let me. Oh, can you enable screen sharing for me, please? I cannot share my screen. Can you allow me to share my screen?
You can share your screen.
Perfect. Thank you. So please tell me once you see my screen. Can you see my screen now?
Yes, we can see your screen.
Okay, nice. So let's start. So hello everyone, and well, today's session will be about two things. I will try to do an introduction to parallel development on computing, and in a second step, we are going to discuss about making parallel calculation with Python. So it means local parallel calculation with multiprocessing and distributed calculation with Dask. And at the end, we are going to discuss how to use something called Python CUDA, so to use NVIDIA GPUs. I will do a few stop here and here so you can ask any question. Since we do not have a lot of time, I will go pretty fast on the generic part, and I will try to slow down on development part, but if you need me to slow down, do not hesitate, okay? And it should be okay. So right now, I am located here in Canada, in Quebec, in Montreal, exactly, so pretty far from you, because for what I understood, you're in Nigeria, I guess. And in normal time, I live in France here at the very west of France, in Bretagne, something called Auray. So not very close. I wish I could be with you today, but it was not possible with family. And yeah, I took just a picture a few days ago. So right now here it's -6 degrees, so pretty cold. Okay, so this training is focused on practical session, okay, because I think that just watching slides is not enough to understand. You have to practice and do it yourself to be able to really learn and understand everything. Okay, so let's start with day one, introduction to parallel computing. I will go pretty fast on that because I want you to be able to practice. So just before we start, there is this website you should definitely check because this guy is working in UK and he made a pretty impressive website full of tutorial on every common parallel implementation. So it means Python, C with MPI, OpenMP, even Python basics, everything is here. So if you want to learn or and become a parallel developer, everything is here. It's not from me. I don't know the guy, so I don't gain anything. But to be honest, it's an impressive website, so you should definitely try it. Okay, so let's start by a few general questions and brainstorming. So what is parallel computing? Basically, it's everything that uses more than, well, one calculation unit, and unit can be anything in parallel, okay, to achieve a parallel processing. So it can be a CPU or CPU core or a SIMD unit, you will see that. It can be a GPU or GPU core, it can be an ASIC, it can be using multiple servers or any other kind of calculation unit. Even a human brain is a calculation unit. You can distribute, I mean, in the old time, teacher asks uh, classes of students to perform parallel calculation together. It's exactly the same. Okay, so basically, if I take a picture, when you cook alone, it's not very fun and it's not very efficient. When you cook with as two, as a couple, it's much more fun and you go faster. And when you cook as a family, you are more calculation units, so you can go even faster and it's even more fun. Okay, so that's the concept. So why do we need parallel computing? It's because you have mainly two difficulties. Either calculation are just too long to be done by a single computer. It will take like years or even months, so it's not possible. Or just calculation need that much memory that it cannot fit into a single computer. You don't have enough RAM memory. Okay, so we need to go either with distributed calculation or distributed memory or just both. So everything that makes your computer burn, in fact. So working with parallel means you are going to use complex technology. You have to understand how a CPU and a GPU work. What is their architecture? You need to understand the concept of network, okay, because you are going to make servers communicate over the network. You need to understand also advanced algorithm because with basic algorithm, mathematical algorithm, you're not going to achieve good performances. Sometimes you need to use a different algorithm because the one you are using right now is not able to be distributed. Okay, so you need to know which technology to use with which implementation for each kind of need. If you do Meteo, it's not the same thing that if you do statistics, chemistry, etc. Okay, so based on my personal experience, here is a good strategy. First, you have to start by optimizing your current code. Okay, don't go parallel first. You need to map your code, optimize, ensure nothing broken. Then you need to ensure your algorithm is parallel able. Okay, you need to change it if not. Then you need to choose an appropriate technology depending of the calculation. So it can be multi-thread, multi-process, GPU, whatever. And then important, you have to go iteratively. I've seen a lot of teams say, okay, we have a code, I want to make it parallel, and they just try to make the whole code parallel at once. And it's a nightmare. You have to go step by step, okay? Segment everything. But we cannot go into parallel before some mandatory hardware and software knowledge. So right now, I don't want you to take any note. You will have the slide later. Just understand the concept, okay? So most people think they can be a parallel developer without knowing how hardware works, and this is wrong. Okay, you need to understand the hardware to be able to do efficient parallel calculation. So here is an example of an HPC cluster. Okay, you have the management node, login node, the firewall and access to the web. You have some storage node. Okay, and you have all your compute node where the calculation occurs. So first, you need to understand that there are multiple kinds of server you are going to face in your life as developer. We have some CPU nodes, so pure CPU based. You have GPU nodes. These are bigger because a GPU is much bigger than a CPU. And sometimes you will see what we call fat nodes, so with a lot of CPU or GPU embedded into a single system. And there are two kinds of network to make all of this communicate. You will see we have an Ethernet network, which is a standard way. And when you have a big cluster, you will use an interconnect network. So it's much faster with big bandwidth, low latency, and you need to use that one when it's available, okay, to achieve good performances. We will come back later on that. So what is a server made of? Okay, this is a picture of a basic motherboard. Okay, basically when you reach an HPC cluster, you have tons of these servers. They can have any kind of shape or design, but the concept is always the same. You have a motherboard with most of the time one or two sockets. And you can see we have memory slots for each socket. So you have to note here that we have 8 slots here for in this example on each CPU socket. This is a CPU socket where your CPU is, and this is where your memory is. And this is the first important point when you are a parallel developer. If I try to make it as a schema, a motherboard has most of the time 2 sockets, so 2 CPU working together, and each CPU has its own RAM memory, and both CPU communicate through what we call a QPI or hypertransfer link. And this is one of the first big rules. 2 CPU are not one big CPU. Even if on the system you see, oh, I see all of the core at once, so it's like if I have one CPU. No, that is wrong, and you need to be careful with that, okay? You need to understand your system. Reason is access to local memory of a CPU is very fast, but the link between both CPU is slow. So if your process is running on one CPU and you need to access its data on the local memory, it's fast, no problem. But if you need to go through the QPI link because your memory is located on the other part, on the other socket, then it will be slow and your performances are going to be very degraded. So this is called non-uniform memory access. So if one day you go with very large calculation on very efficient calculator, efficient HPC cluster, you need to take that into account. Okay, so be careful with that. And it's a common trap. Most users think, hey, I have a big server with a lot of CPU. I can just add cores to make it parallel and improve performances. No, that is wrong. Because if you increase too much, where is my mouse? The number of cores, you will see that this is a perfect multiplier. Okay, basically, if in real life, if in perfect life, I will add more core, I will have a perfect scaling and performances. But in real life, when you go too large, at some point you reach a maximum, and after that, most of that it degrades. Okay, or it just stalls, so you don't gain more performances, but you lose power and you lose. I mean, you just use resources for nothing. So just be careful when you do parallel computing, benchmark your calculation to check at which point you should stop. Okay, so this is a major rule also with parallel. So let's speak about CPU. Okay, we have two major kind of components here, CPU and GPU. Let's first start with the CPU. So this is a standard CPU you will find in most HPC cluster. So when you remove the what we call HIS, we have inside the CPU itself, the die, and this is what a CPU look like. So basically here it's a standard CPU you have in laptop. You can see the cores. Okay, so we have 4 cores here. So basically if we do parallel calculation with CPU, we can use 4 cores. So we can expect at maximum 4 times faster performance than a standard single core performance. Okay. Also observe that the CPU cores are pretty big. Okay, we will come back later on that. So the first parallel unit, and it's most people don't know it, and it's a pity because it's very efficient. The first parallel unit you can use is hidden inside CPU cores. In each core of your CPU, you have something called single instruction multiple data, or SIM unit. So this is a CPU microarchitecture. And if we take a look here, so this is where calculation are occurring, okay? If we take a deeper look, you can see we have something called vect, okay? Vect string, vect value, vect multiplier, FMA, etc. And these units are made to do parallel calculation inside your single core. Basically, when you do calculation on very large arrays of data, like matrix or vectors or, Like if I have if I do CFD, so computational fluid dynamic, I have a large field of temperature, and I need to do some calculation on that. When you do the same exact operation, mathematical operation on each data, so it's a massive amount of same calculation, then you can use the SIMD unit. So basically in one cycle, calculation cycle of your CPU, instead of doing one um, item at a time, it will do 4 or 8 items at a time. Okay, so this is a parallel calculation that occurs inside your CPU. Most people don't know that, but the performances you can obtain are extremely great. If you know how to use them, this is impressive. For example, here, without optimization, we have the blue one. When you use SSE3, so it's an old SIM one, you have much greater performances, and with AVX2, so latest versions, you can see we have a very large increase of performance. So this is only if you do massive calculation on vectors or matrix. So basically it's just that, okay? But you need to know that. It's very efficient, and this is parallel calculation inside your CPU itself. This is for CPU. Now let's speak about the GPU. That's another unit, okay? So basically today on HPC market, most of the time it's NVIDIA because they just kind of win all the deals. So if you compare a CPU, remember, with a large cores, with a GPU, you can see that the architecture is different. A CPU has few cores, but they are very big. A GPU has a lot of small cores. Okay, so if you compare them, the GPU is much bigger with a lot of tiny cores, while a CPU is much smaller with big cores. Okay, so if we take a deeper look on how it is made, we have a lot of small cores, though, in green, okay? And these are called SM units. We will speak about it later when we will work with Python CUDA. Okay, so reason of that architecture is because GPU were made originally for video games. Okay, and in video games, it was massive pictures uh, calculation. So main one was anti-aliasing. So when you take here an example, you can see we have a lot of pixels, and when you use the GPU anti-aliasing mechanism, it's kind of, perfect rendering. And so that's an aliasing on anti-aliasing. And these are massive matrix calculation or kernel calculation. You just apply the same kernel of calculation on the whole picture to filter it and obtain something clean. And this means you are doing a massive amount of small calculation on massive amount of small of data. Okay, for each picture at 60 pictures per second, the players wanted to have something nice. So the GPU was designed to do a lot of pictures calculation. So that's why you have a lot of small cores, because it's not complex calculation like with a CPU. It's small basic calculation, mathematical calculation, very small one, but ton of them. So they choose to use a lot of small cores to do that. And well, we have a lot of other different stuff. Okay, so I'm not going to do a demo right now. So if you compare again a CPU and a GPU, you can say, well, my CPU is a big unit, a big insect, okay, complex, robust. And on the other side, a GPU, you can see that as an ant colony. Okay, a lot of small ones, but together they achieve extremely great performances. So that's an example also of a Samsung die from a smartphone. I took that. I think it's interesting to understand. You have the exact same. You can see the CPU cores here are big. Okay, you have one big core here, three medium cores, and four small cores. Okay, and this is the GPU, and we have tons on the very small core. So a smartphone CPU GPU is exactly the same. When you take your smartphone, like my old one here, and you just start it, and there is a picture on it, all the picture is rendered through the GPU. So a lot of small pixels to calculate. That's exactly the same. Okay, so last part I want you to know about hardware before we start is network. We have two major kinds of network in HPC. We have what we call Ethernet network and interconnect. Okay, so the Ethernet network is used mainly for administration, and it's very slow. Okay, we have a low bandwidth and a high latency. So on some systems where the systems are very small, you don't really care. You have just an Ethernet network, and that's enough. But when you have a huge HPC cluster, you need much greater performances, and then most of the time you have something called an interconnect. Okay, so it's a very efficient proprietary network. Most of them right now are from Mellanox company, so it's called InfiniBand. And these networks are driven by a subnet manager to optimize communication. Okay, so when your calculation algorithm need to communicate over the network with neighbors, you know, to communicate data, you just have to be sure you use this network. Okay, so just contact your local system administrator and be sure with him that you use this network to get really good performances. Okay, just one last part about on the software side, you need to understand the difference between a process and a thread. Okay, so this is a process I try to represent. A process is a software element that has an ID with in the system. So you can see when you start something on Linux, if you use top command or ps command, you can get the exact ID of all the process running, and you can see the ID of your process. So this process has a main thread running, okay, and it has some memory allocated to this process. And sometimes when you do parallel calculation, you start threads. Okay, these are threads. These threads are some execution elements you start that stay inside the process scope, so they share the same memory than their father. Okay, just that the thread zone can distribute across the core of your CPU, so you can use all the cores to perform calculation. Okay, so thread can access further memory, but process cannot access memory of another process. It's isolated for security obvious reason. Okay, so you from one process you cannot access data from another process. If you want to do that, you need to communicate. So that's communicating through local system or from the network. If I have one process running on one server, another one on another server, I need to communicate through the network, which implies latencies and development. Okay, so you will see that, for example, with Python parallel, we are going to use multiprocessing, but it will be very similar to multi-threading. And with Dask, so distributed Python, we are going to use network to communicate. So that's different. Okay, so that's an execution, for example, here in one process through the time, you can see data, all threads can access data of their process, but I cannot access data of another process, basically. Okay. So if you do multi-thread calculation, technology are OpenMP, pthread, Dask, or well, CUDA, it's in the middle, okay? But OpenMP, pthread, or Dask. Dask can also use multiple thread. And if you do multi-process calculation, so not multi-thread, but multi-process, most of the time you are going to use MPI or Dask. So these are the implementation available for you. And sometimes you do both at the same time for scaling with reason. So it's called hybrid calculation. Okay. Okay, so I'm not going to cover that. We will come back later to this. Just beware, not technology fit with all mathematical problem. Okay, so if you use MPI, it means you distribute memory. It's not suitable for all algorithm. And if you use CUDA with a GPU, it's efficient for massively redundant operations, so a lot of small ones, but it's not made for uh, very specific calculations that have a lot of conditional, for example. Okay, so you have to find the best suited algorithm according to your need and your skill. Okay, because you cannot, like for example, if you want to use CUDA, it invests a lot of skills. So it may not be the best way to start, for example, okay, except if you have really something that just fits perfectly for it. So that's all for the hardware knowledge. So before we continue with parallel, do you have any question? No? Everything okay?
Do, do you have any question?
I
Please,
know it's fast, sorry for that.
is anyone having question from the Zoom platform? Okay. Online. Okay, hold on.
Yeah, hello, can you hear me?
Hello?
Yeah, so I would like to ask about communication between cores,
Hmm.
communication between clusters. You said you can either use Ethernet or interconnect,
Yeah.
right? So I know about Ethernet, but that interconnect, can
Uh,
you please elaborate better?
can you repeat the question?
Yes, I want to know the difference between the Ethernet and interconnect.
Okay, I see what you mean. So let me go back few slides. I'm going to describe that. So basically, yeah, that one. So you can see this is that one. Okay, this is an interconnect card. Okay, so it's dedicated card with specific cable, and looks like that one. Okay, so the concept is the following: with Ethernet, when your data need to communicate from one process to the other one, you have a lot of steps. It needs to be copied from memory to CPU, kind of translated to TCP, okay? Then it goes to your Ethernet card. There is some latency to communicate with the others. Say, hey, here is my data. Okay, how I can do it, blah, blah, blah. Then the data is sent as small, a lot of small package, okay, to the other one. And on the other side, they need to translate it. It goes through the CPU, then to the memory, etc. So it involves a lot of time. On the other side, with interconnect, uh, it's kind of integrated. You have to load kernel module to use that. It uses something called RDMA. So basically, everything is hardware accelerated and your data is copied directly from memory to the card itself and just sent as a huge package. It uses jumbo frames, so very big slot with optic fiber. So everything is completely hardware accelerated. That's why, for example, here on this card, you have some dissipator because you have some. It's not like a small Ethernet card with no dissipator. You know, it's very small chip. Right now, here you have a lot of hardware accelerated calculation, and the cards themselves communicate with intelligent switches that tries to optimize the number of hop, okay, to reach your other servers. So basically, what I could say is that if you compare latency on Ethernet with 10 gigabyte net Ethernet, which is already a very performant one, you have like 30 to 100 microseconds to communicate with each chunk of data, and on interconnect it's 1 microsecond. So much faster, because when you need to communicate the data from one server to the other one, it means that during the communication time, your CPU does nothing if it's not optimized, okay? So with that, you just reduce the delay between communication, so you use much faster your CPU. It's much better. Also, you have a very much greater bandwidth. It's like, well, the latest version HDR, it's insane. It's like 200 gigabytes per second. It's completely insane. Very efficient. You see what I mean? But it costs a lot of money. So you don't have that on small cluster. It's very for big clusters. Did I answer your question?
Hello, can you hear
Hello?
me?
Yes, perfect.
Okay. Uh, at the beginning of your presentation, you show a graph where there is a relationship between the numbers of cores and the operation of
The
the
cluster.
cluster.
that one?
Yeah, that's that one. Okay, I would like you to throw more light on it so that we understand it better.
Yes, of course. So basically, when you distribute calculation, okay, let's say, oh, I have a good example I will show you later, but let's see it that way. If if you take a lot of students in a classroom, okay, you are the teacher, you have a lot of students, let's say 20, and you are going to say, okay, I have an array of data I want to calculate, and I want to distribute this array of calculation across all students. So if you are smart, you are going to say, okay, I have 20 students, my array is like 100 elements. I'm going to give each student 5 elements to calculate. So each student comes to you, takes their 5 elements, and go back to their desk, do the calculation, and that stuff. But the computer is not smart. So basically, it's going to say, hey, student 1, take 1 element. Go back to your desk, student 2, take 1 element, etc. And you are going to spend all the time managing the student. So that's a process with the thread. And, well, it's exactly the same here. If you have a calculation to perform, and if you have too much process or thread involved to communicate, at some point it's a mess, a huge mess. Okay, it's like with companies. When you have a small company, most of the time it's very efficient because everyone communicate fast and work together. When you have big companies with a lot of levels of management, it's slow, like it's horrible. Okay, and that's exactly the same here. If you do a calculation, the more cores, so the more thread and process you add, at the beginning, you get better performances. But at some point, when you add too much, you start spending so much time managing them that you lose the benefit of it. Do you see what I mean?
Yeah, I see what you mean. So, if I understand it, it's like if we have a lot of calls and we do not
Yes.
have a lot of data to be processed, okay,
Mhm.
that's what's going to make the whole thing a little bit lower in terms of performance, if I understand.
Exactly.
Okay,
Exactly.
okay,
Yes.
thank you.
You need really to have something to feed them. I mean, it's just not worth it if not. So most of the time, the best way to go is to say, I have my parallel code. I have this kind of data. You just do few benchmark calculation with an example of data you know you are going to do for very big calculation. You do few calculation, adding more and more cores. You do this graph, this scaling graph, and you check at which level you should stop. And this is where you will get your maximum performances.
Okay, thank you.
You're welcome. Just one last point. Uh, this this part when everything slow down,
Questions. Okay,
it happens sometime
you
when
can
you
stay
start
in that
using the
slide.
QPI link.
Mm.
Yes,
Okay. I want to know that if this curve, this plot, is depending on the under laws for calculating
it's
the speed
depending
up.
of. So you mean what affects that?
Because when you add the number of
Of
code,
course. Yeah, here.
it at the point when you where you put the vertical red lines,
Yeah,
we have the limit calls to speed up for maximum speed up.
for your current calculation on data set,
Yes.
yes.
Why we have the curve going down now after that? Normally the
Oh,
curve should be constant.
so it depends. Sometimes with some calculation, it's constant, okay? But sometimes, as I said, you start managing so much thread and so much process that, I mean, you spend all the time doing that, and you just drop performances completely. Okay, and that's not the only element that can affect that. Let me take another example here on that slide. If, let's say here I have 4 cores on each CPU, okay? If I start my calculation here and I use 1 core on my memories here, good performances. 2 cores memory here, good. 4 cores memory still here, good performances. But let's say my calculations are so much memory bound that when I start with 5 process or thread, and that part of my memory need to go through the QPI link to be reached, then my curve starts being impacted. Okay, but that's not the only thing. That's exactly the same when I start involving network. If I start going outside of my server, because on my server I need more cores, as I start involving the network, then it means each time I need the data from another server, it takes time to come back. So again, I start impacting my scaling curve. And let's say now all my servers are on the same switch, the same InfiniBand or Ethernet switch. When a server communicates with another one, it's just one hop to be reached. But let's say I used all my servers on this single switch. And now I still increase the number of cores, so a lot more servers. I need to reach data on servers that are on another switch. It means that to reach them, I have to go through my switch, then do a hop to the other switch, then reach them. Again, it has some impact on scalability. So you have a lot of things involved that can impact your scalability. But one thing is sure, whatever the algorithm, except what we call embarrassingly parallel calculation, because these one just don't communicate. But if you need to communicate data, at some point, the scaling is always going to go slower or even drop. Does that answer your question?
Yes, I understand. But what something that is not clear for me is when in your plot you put in the y-axis, the vertical axis you put performance, and we don't know what metric is used to
Oh,
plot the performance.
it's well, basically it's just the calculation time here. Okay. If let's say I try to find the number of prime number of a range. If I use 1 core, it uses 20 seconds. Okay. If I use 2 cores, it takes 10 seconds because I divided the time by 2.
It is
4 cores, it takes 5 seconds, etc., etc. So
it
that
is
would be the
it is
perfect scaling.
the speed up.
Yeah, exactly, the speed up. Yes.
Okay, because according to Amdahl laws, the speed up when you have the maximum CPU for uh, uh, increasing the speed up. After that, normally the curve became constant. But when you try to add the delay according to the network, you can now have the performance decreasing. I don't
Yes,
know if you.
it depends. Yes, I see. It really depends on the algorithm. Here, I wanted to show that it has an impact. But yes, some will go that way, and some other will go that way. Sorry. Some other will do something like that. You see what I mean? So they will kind of. I'm going to remove that point. How can I remove it? Yeah, so some others will do something like that, like flatten.
Mhm.
Okay. It really depends on the algorithm.
Okay.
But one thing is sure, at some point, increasing the number of core is not efficient. Because if you just, even if you flatten like that, it means that you use energy for nothing. You see what I mean?
Okay. Thank you.
Yeah, you're welcome. But you're right, it depends on the algorithm. No other question?
Benoit. I'm just
Yeah.
wondering if there's a benchmark with respect to either the CPU or GPU that tells you the size of data and the corresponding cores that will give you optimal performance, so that that can be a guide when you are trying to.
No,
Okay, there's no
no,
benchmark.
there is no.
There's no
No,
benchmark.
because
Okay.
well, the reason is it depends of your own calculation. I mean, it really depends of the algorithm you choose. Let me take an example. If I do some what we call conjugate gradient calculation, for example, to solve the Poisson equation, I will have a very different scaling than if I use the multi-grid method or Gauss-Seidel. Or, I mean, it really depends. So the best benchmark you can do is take your own code, take some, let's say I want to do a CFD calculation that is going to take 1 week of calculation on the whole on a huge part of the cluster. It's an iterative calculation. You know that it iterates over the time. The best way to work is to say I take my code, I take my input data. This is the input data I'm going to use for my final calculation, and I just start and say to the calculator, I want to do 10 iterations and just stop. Then I increase the number of core on server, and I ask again 10 iterations, I start, etc. You do that, and once you found the best set, okay, so the maximum scaling that fits for your execution, you say, okay, now do the same, but with all iteration for my whole calculation with the perfect core level I found. That's just a matter of benchmarking your own code. And just one last thing, never trust marketing guys. Okay, they will say you all the time, hey, don't worry, it will scale. No, that's not true. In real world, it's not scaling. Does that answer your question?
That's very clear. Yeah. Thank you.
Okay,
Yeah.
you're welcome. So, no question? Okay, so let's continue.
You can go ahead.
Okay. Okay, so step one, when you want to start, you have your serial code, it's working, you want to make it parallel. Okay, first step before going parallel is to optimize your code. Okay, so first thing to do is map your code. So there are a lot of mapping tools. The most popular open source one is called Valgrind, but you have also Intel vTune or a lot of this. So a mapping tool allows you to identify critical section of your code, to know where you should focus first. Sometimes you can be surprised by what you are going to find, okay? And also it helps you identify unexpected bugs, because these tools are going to closely monitor the execution, and sometimes they will find bugs you didn't suspect, okay? So Valgrind, for example, is an open source tool. You have the KCatchGrind to visualize the results. And just be sure to build your code with debug flags to obtain correct output, because if not, you will just see numbers, it was nothing, okay? And also interesting thing is that at the same time, Valgrind is extremely strict about bugs, so it may identify a lot of memory corruption or stuff like that. So this is an example of a code mapping. So you are going to see the whole code executing and where exactly is calculation occurring, where is everything, okay? So that's the first step, to know exactly where you should focus, and maybe if you have some bugs, identify them, okay? Then you have to optimize, okay? So just first thing is just to ensure your code runs fine into a debugger. So no bug, no major bug, okay? At least something obvious. Then you have to use native compiler optimization, okay? Just beware some optimization reduce precision. So it's not a matter for many code, but some code may be impacted by that. When you have a lot of cycle to execute, sometimes your precision is going to suffer. Okay, so just refer to documentation. Then optimize the loop. Okay, so move out of loop any unneeded operation, because you will see that most of the time when we develop, we don't really care, and we put a lot of things into the loops that could be done outside of the loop. Okay. Also replace AV calculation. It might be surprising, but when you multiply by 0.5, it's much faster than when you divide by 2. Okay. So if your compiler is smart enough, he's going to do it for you. But it's just an example. But sometimes it's worth, you know, inverting few things. Of course, limit I/O and use buffers. So try to avoid writing, reading, opening file all the time. And just be extremely careful of memory striping. If you use C or Fortran, be extremely careful with that. The memory is not organized in the same way. It's the complete opposite. So when you loop over your arrays, if you don't take into account striping, the impact can be extremely important. Okay. Also avoid, if you use a lot of temporary work array, avoid allocating, delocating all the time. Use work arrays and just allocate them at the beginning and reuse them, okay? Empty them, reuse them, but allocating memory and deallocating text type. So that's a major rule. Before going parallel, you need a clean code, okay? Be careful, because you don't want to mess with bugs when you go into parallel. It's a nightmare to debug. Also, that's a good time to do advanced optimization. So you can use external mathematical libraries, so FFTW, MKL, LAPACK, blah, 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 a lot of them. And even some of them are already parallel able, so you can take benefit of that. That's the step also to ensure you are doing your SIMD unit, okay, inside your CPU, okay? So that's a two-core unit, and you can see the SIMD here. So that's a good time to be sure you use SIMD if your calculation can use them. Sometimes it's not usable for you, but if you can use them, just be sure you use them. It's very efficient. And also try to do some asynchronous I/O operation, like, I want to write a file, I don't want to wait for it to write, it's too slow. So you just say to your code, okay, write that file and just put that into a separate instance thread, and I continue to work in the meantime, and I check later you have finished. So just a few words about SIMD unit, single instruction, multiple data into your CPU. Most of the time with a clean code, so just you don't most of the time you don't have to to optimize your code too much. Just provide a clean code to the compiler, and the compiler is going to use SIMD natively, okay, for you. If he's able to understand what you did, he's going to use SIMD because it's made for it. Just be sure to ask for GCC, for example, minus all 3 and m arch equal native. Okay, when you do that, your binary generated is bound to your current hardware, so to your current CPU. You cannot use the same binary somewhere else, but at least it's optimized for your current CPU, so it's going to use your CPU SIMD unit, if available. So that's the first step. Step 2 is to ensure you have a parallel able algorithm. Okay, so let's take an example. I do matrix operation with 3 diagonal matrix, and I'm going to invert them. And I use the very well-known Thomas algorithm. That algorithm is not parallelable at all. It's not possible to make it parallel. So you have to change. Okay, you have to choose another algorithm. Sometimes there are no way to parallelize your calculation. That's life, so you have to deal with it. Sometimes it's possible. So right now, I can replace Thomas' algorithm with conjugate gradient algorithm, for example. And that one is known to scale pretty well. Okay? So that's how it works. It's a very interesting algorithm. And sometimes, again, if you document a bit, you will understand that when you combine multiple methods, it will have even better performances. So if I precondition my conjugate gradient with a multigrid method, I will have a much better performances, and so it will have a much greater impact on my calculation time. And again, if I use multi-grid algorithm to preconditionate my conjugate gradient, if I document a bit again, I can see that using double use cycle like this one, I increase a lot performances because I reduce a lot the number of iteration. So that's a very important step. I know you want to develop, I like it too, but if you don't document a bit, you are going to miss a lot of important things, okay? So choose carefully your algorithm, discuss with experts, and maybe sometimes try to optimize, okay? I mean, a lot of things need to be done, a lot of things needs to be invented, but at least document a bit, it's very important. Also note that a lot of algorithms already were parallelized by someone else, so maybe there is a library available for you to use it. So then you don't need to redevelop everything. That's cool. If no library exists, then you can try to exchange with other teams. Maybe another teams already did it and they are okay to share this part of their code. Okay? But if nothing was found, then you need to go with developing yourself. So step 3 is to choose the appropriate technology. Okay, and that's a key point and you need to understand. If your calculations are called embarrassingly parallels, it means that your calculations are natively parallel. Okay, so an example, if with statistics, you are going to apply the same calculation on a lot of sets, independent set of data, okay, we call chunk, then it means you do not need to communicate. So it's natively parallel, you can use anything you want. So first question, if not natively parallel, is can I split my memory? Some algorithms do not allow you to split memory. Sometimes you need to have access locally on at all data. So if it happens, then you need to go with shared memory. So it's OpenMP, my Python multiprocessing, things like that. If you can distribute, you can try to use MPI or Dask to, to have greater performances and be able to use larger cluster. Second question is, can I use a GPU architecture, okay? And do I have some at disposal? And do
Hello,
you have the
Dr.
investment
Benoit.
possibility? Yes,
We have a question from an online participant.
yes.
Okay, so let's take the question. Benjamin, one of the online participants, can you give us your question now? Or mute for him.
Sure.
Okay, go ahead with your question, Benjamin. I can see. Benjamin Maxwell, unmute and ask your question. Okay, you may, okay. His hand is down again. Okay, maybe we'll continue. But you can just put
Okay.
your question in the chat box. Put your question in the chat box, then later we can come back to it. So,
Okay.
Benoit, you can go on.
Okay.
Yeah.
So yes, if you go with a GPU, you have to know that it's much more complex to develop, but well, you will have great benefits at the end with performances. And the last step is, okay, now you know what you want to do. You know the algorithm you are going to use. You know the language, you know the implementation. So you go with parallelizing your code. You need to go iteratively. I have seen so much team say, okay, we are going to parallelize everything at once. And it's a nightmare, okay? It's not that easy. So just look first at, at where you should do optimization, when you should parallelize, okay. Also do a test case to be able to compare your result with serial code, okay? Because it's very frustrating to develop something and say, okay, it works. And when you compare with your serial execution, you don't have the same result. So it means there is a bug somewhere and it's difficult to find. So instead of that, do the comparison all the time to check your calculations are still the same, okay? And a good way also is to isolate the needed part of the code, make it parallel, ensure it works, and then merge it and continue like that. So go iteratively, okay? Simplicity. It's already complex enough. So right now I'm going to do a last quick overview of implementation, parallel implementation available, and we will go with Python parallel, okay? So first, I'm going to discuss about what is available with C, C++, Fortran, and the first one is OpenMP, so for Open Multiprocessing. So it's very simple to implement and use. Okay, so it's easy, you don't have to do a lot of modification, but if you don't use it well, it can lead to very poor performances. Okay, so basically, you just have some parallel region when you say, okay, for this part of the code, I know it's going to take a lot of time to calculate. So I want this part to be the parallel part of my code. So you just spawn thread, distribute the work, do the calculation, and then join together and continue execution. It's very simple. You will see it's just pragma to be put into your code. So if you understand it pretty well, you will have good scalability, and it's pretty easy to use. But be careful, it's treacherous. If you don't use it well, performances may be not very efficient. Okay, so this is an example right now with very basic code just to say hello in C. So we just say, okay, this is this part was serial, this part was serial, and in that part, it means it's a parallel region. So everything here will be executed in parallel inside that with different threads. Okay, so if I execute that with GCC, and I say I want to use 2 threads, I'm going to get, okay, hello world from thread 1 and 0. And if I ask for 4 threads, hello world from 0, 1, 2. So you can see also that you do not control the order of execution anymore. So you need to be careful with that. You can see that 2 went before 1, etc. So just, again, all of this happened in parallel. It's not one after the other. It was just everyone at the same time. So right now, let's say I have a very, let's say I have this for loop that takes a lot of time to calculate. I can just make it parallel this way. And if I do that, basically what is going to happen is that some threads are going to be created, and the for loop is going to be distributed across all my threads to calculate. So each thread is going to map to one CPU core to use all my CPU cores available. Okay? And at the end, they are going to join result. Because again, we are in OpenMP, it means we share the same memory. So if everyone fills the memory, at the end, you have the result. So just beware of basic trap with OpenMP. Since threads share the same memory, you have to prevent race condition. You don't want everyone to write at the same variable at the same time. So you need to make some variable private to thread and some shared. And also ensure you manipulate the scheduler. As I said, for my for loop here as an example, I don't want every thread to take one value to calculation, come back to master thread, say, hey, I want another value, and take one value, etc. So it means they are going to spend all the time managing the thread. Use the OMP schedule variable to say, no, I want my thread, for example, to get a chunk of 20 data, do this calculation alone, and then come back to master thread to get another set of data. Okay? A few resources, again, the Christwood website has a lot of things if you want to learn OpenMP, and you have also other training available. Again, the slide will be provided to you, so don't bother writing down the link right now. I don't really have time to do a demo. If we have time at the end, I'm going to do one, okay? But everything is provided. I'm going to provide you the training to do on your side just after, and everything is described, so don't worry. So OpenMP is limited to shared memory and a single server. If you want to use greater power and spread across server, you need to use MPI. So MPI stands for Message Passing Interface, means we are going to communicate between process through the network or locally to exchange data. Most famous library on runtime are OpenMPI, MPH, MVAPH, IntelliPI. MPI is a standard, okay? So all of these are implementation, but MPI is a standard. Okay, so it allows communication across the network to send, receive data, and it's just be careful because many students did the mistake. OpenMPI is the name of an MPI implementation. It has nothing in common with OpenMP. OpenMP was what we have seen before, you know, to distribute load across thread. OpenMPI is just the name of an implementation of MPI, but it's absolutely, the name is close, but it's absolutely not the same thing, okay? So MPI, for example, share communication, do communication through the network, okay? So I have all my process and they exchange through the network. So if I take an example, here is a picture. So these are pixels of my picture, and I want to do a blur operation on each pixel. So it's an average value of each pixel, okay? So if I have my memory on a single system, it's easy, I do my blur on all the dots, that's all. But let's say my picture is sliced in two parts with MPI on two different servers, then how I am going to calculate that part, because that data is here on the other server. Remember, my picture is sliced in two parts. With MPI, I'm going to create ghost, means I'm going to have a local copy of the other process. So I'm going to communicate and grab a copy of that one into my local memory. And the same apply on the other. This one is going to send a local copy of its boundary to the other. So at the end, everyone will be able to do the whole calculation. Okay, so that's basically how it works. You communicate through the network chunk of data. So most of the time, we exchange data through Ghost, and once it's done, you can apply your calculation to the whole field. Okay, if needed, you can do asynchronous communication. Okay, sometime when you do optimization, you can do asynchronous communication, so your CPU calculates part of the field while you communicate, and at the end, your CPU finish the boundaries. Okay, but you should go with that later when everything is okay with synchronous communication. Again, step by step. Okay. So MPI is the way to go if you want to go with large cluster, but it needs much more investment than OpenMP because you need to communicate and you need to handle your self-communication. Okay. But on the long term, it's worth it because you are going, if you do calculation and later you want to do greater calculation, with MPI you will be able to use very large cluster. With OpenMP you are bound to one single server. So on the long term, it's worth it. And if you need to do both, sometime you will see to improve scalability, you are going to use both OpenMP and MPI together. It's called hybrid calculation. So most of the time, you have one MPI process or two MPI process per server. They create OpenMP thread to use all the core of the server, and the MPI process communicate through the network. Because it's more efficient to have one guy speaking for the whole team locally to the other team than every guy from the team communicating with every guy from the other team. It's going to be a mess. You see what I mean? So that's why hybrid calculation is interesting later. Again, some resources if you need. Then let's speak about Python multiprocessing. I will go quick here and come back just after with much more details. Okay, so Python multiprocessing allows to do shared memory calculation. So it's kind of similar to OpenMP in a way, but a little more complex. So Python does not handle multi-threading well, so we need to rely on multiprocessing to cover the gap. Okay, so this is an example here. With Python, you can import multiprocessing. You create a pool of process simply, and when you need, you execute the calculation on the pool of process. So right now, I executed this example, and it says, okay, my worker, this one said hello, and you can see here, it's the PID. So again, it's the ID of the running thread or process. It's another one, so it means we have two items working together. Don't worry, we are going to do that later. In Python, another one is Dask, very well known. So Dask is a solution to distribute Python calculation on many arrays. It's really made for arrays of data on large clusters. So you can use Dask on your local system if you want, but you can use also on HPC job scheduler. You can use SSH to work on the cloud, on Google Cloud, Azure, AWS, etc., etc. So it's very efficient. So this is an example right now how to execute NumPy arrays, for example. You just connect your client. Here it's a local client, but you can use something else, a distributed one. And you can perform your calculation kind of like usual, and it will compute them over the network. Okay, so I'm going to go into details just later, don't worry. And last part is CUDA. That part is a bit different. So you need an NVIDIA GPU. So if you use this technology, you are bound to NVIDIA. You need to know that. It's not a big deal, but you need to know that. And you need to have calculations that match GPU architecture, but the power gain is very significant. Okay, if you succeed developing on CUDA, the amount of power available is insane. Okay, it's really, really efficient. I don't know if. So this is an example. We speak Python CUDA, I will come back later, but basically what you need to do when you perform with CUDA, you need to allocate memory locally on your CPU, you need to allocate memory on your GPU, and you have some memory copy from your RAM memory to GPU. So that's for standard CUDA. Now, recent version can directly pick memory inside the RAM, but for standard usage, you have to manipulate data, then execute and get data back later. Again, with Python CUDA, and we will see that. A small tutorial if you want to go with that. So that's the end of my introduction to parallel computing. We'll do Python just later. So there are more implementation available. Okay, so target was just to show you what's pretty standard. Just once you find the implementation you want, once you are learned one, all the others should be simple, because once you understand the concept of parallel computing, I mean, using other implementation is not that difficult. My recommendation is start with, if you want to learn, start with local parallel. Don't bother with distributed on different servers for now. And once you master that, go with distributed. And a good way to start is to play with Bash script. I provided an example in the training in this session, you will see. It's a good starting point because it's very simple and interactive. So just remember the key point. You have to understand the hardware. It's an absolute mandatory skill to be efficient as a parallel developer, and understand that parallel computing occurs at many levels. It can be inside the CPU with SIM, per CPU, so the cores, per socket, so you have to manage the NUMA, and GPU with many cores. And at the server level with network, so Ethernet or interconnect if you have one. Also, the mathematical algorithm you choose are key to good performances. Okay, so performance and distribute memory and calculation. So just be sure to use a good algorithm. And when possible, try to use popular parallel libraries. A last small tip, if you really want to involve into parallel computing, a good way to start learning is just to use VM or just buy second-hand, because you have a ton of second-hand Raspberry Pi on the market, so it's very cheap. Just buy few Raspberry Pi, a cheap Ethernet switch, connect them together. So just be sure to grab a Raspberry Pi 3. They are cheaper, or 4 if you have more money, because they have multiple cores. So it's perfect to learn and simulate distributed calculation, because you have 4 cores in each Raspberry Pi, and with the network you can distribute calculation also on the network. It's a very small cluster, a sample that is very interesting to set up. It's cheap if you use second-hand, and I did one myself, and it's very simple. So if you want to learn parallel calculation, that's a very good way to start. So just before question on that part, before we go with Python parallel, I made a tutorial at this link so you can learn basic parallel implementation. These are examples for you to learn, so you can choose which one you like. Since we are limited on time right now, we are not going to do it right now. I'm going to cover Python parallel and Python CUDA, and then we can do the whole parallel programming at once, okay? Do you have any question on this part before we start with Python? We can do a small break of 10 minutes also if you want.
Hello, Benoit. Thank you for the.
Hello?
Hello, are you hearing me?
Yes, yes,
Okay,
perfect.
thank you for the lecture. I think in this lecture you skip the software part where you should have introduced the software, because at a point I was getting confused about the thread and the process. Please, can you go back to again?
Yes.
Thread and process. I was getting confused about it, and so the remaining part that you were talking about, mapping, the Python part, I'm just trying to picture what you are saying there.
Yes, yes,
So please,
no
can you help
problem
me?
with that.
Thank you.
Sure, sure. So this is a process, okay, here. For example, I am on Linux. Is it big enough? Can you see my screen here? I don't know if I can increase the size. Settings. Oh, come on, it's so slow. Can I increase the font a bit? No, it seems not. It's. No, I cannot change it. Okay, well, anyway. So, yeah, I can zoom that way. Okay. Is it big enough this way? Okay. So if I start a sleep command, and I ask my system, hey, I want you to list me all the ID running on my current system, you can see that when I started it, it says, hey, this is the ID of my process. So each time you execute something on Linux or on Windows, it's exactly the same. Each time you start something, it will start a process. Okay, a process have what I could call a main thread, so a single unit that execute. It has some memory dedicated and some other stuff like an ID, a kernel state, register, but we don't care. Just memory on one master thread. A thread is something, you can say it's a worker, okay? You can think that as a worker. So something that do calculation. So we have one calculation thread and a memory, so that everything is part of a process. A process is able to create thread. Thread are more calculation items that are still in the scope of the same process. So they share the same memory. Okay. If I take an example, no, not that one. Oh my god, I clicked on it. Sorry, I need to close it. Okay, if I take an example, I should be my MPI call. Okay. So this is an MPI code. It's going to use multiple process, okay? If I execute it, oh, I forgot one. Okay, anyway, MPI. Okay, so I created two processes, and these are fully isolated process. It means that their whole memory was isolated. Okay, so they just can communicate through the network or another way, but they cannot access memory of the other one. If I go with OpenMP, that one, execute it. I have three, oh, I call them process, it's stupid for me. I have four threads working together. So it's difficult to, I mean, in fact, it's pretty simple. A process is just, you know, it's an entity that can have multiple threads. It's like a family, in fact, okay? They share, you have the process, so the main thread are the parents, and the thread are the children. They share the same home, so same memory, and if one of your children want to share a book with one of his friends at school, he needs to take it from your home, go to the school, and share it to the other children, which bring it at home. And these are kind of family. You can have multiple threads that can execute and distribute load over the different cores of your CPU, but everyone is as a family. They share the same memory. You see what I mean? I cannot hear you anymore. Do you see what I mean by that?
Yes, yes, thank you.
Sorry. Okay, cool. So that's why, for example, some calculation needs to be done via thread instead of process, because some mathematical algorithm needs that you have the same memory available for all calculation workers, okay? And on the other side, if you can slice, so distribute your memory into small parts, you can go with multiple process because they can communicate to work together, but they can use their own memory to do calculation. No other question? Okay, what time is it? 11. If you want, we can do 5 or 10 minutes break so you can digest. Sorry for that. And we can start with Python parallel after that. Is it okay for you?
Yes, that's okay. Thank you very much. So we are coming
Okay.
back.
At 20, 24, 25.
Okay. So we can digest what has been passed across to us.
Yeah, sorry, it's a bit fast, but well, I have to deal with it.